if you look at this proposition that we have now, this should remind you, this should remind you about, this should sort of like, remind you about, what we talked about, or it should remind you of what we talked about in when we're talking about, during the summer when we're looking at Algebra 1, les ensembles. We talked about les ensembles. Now let me remind you, one very important, part we did that is going to sort of like help us understand what is happening here is the aspect or the idea of what is known as l'image directe. L'image directe. So let's first of all look at what is known as l'image directe. We said l'image directe is, let's say we had some set, let me remind you, we had some set E. This was the parent set. E was the parent set, and then A was some subset of E. Then we said that l'image directe, which is F de A, is the set of all elements F of X such that X is an element of A. That is what the l'image directe is. So l'image directe, we said, if A is a subset of E, if A is a subset of E, then l'image directe, we defined l'image directe as the set F of A such that F of X, we defined l'image directe, which is F of A, as the set of all elements F of X such that X is coming from the set A. And then same thing here. Instead of talking about sets, we'll be talking about les espaces vectoriels. So this E that we have here is an espace vectoriel, and then we have A, which is a sous-espace vectoriel. So you can sort of have the same idea, have the same thing. Okay? You sort of like have the what? You sort of like have the same thing. Now, having said that, then we can now come to this particular concept, that we have here. Donc, soit E et F, deux cas espace vectoriel, and I just forgot to tell you that we have sets for everything in mathematics. We have sets for everything. We have a set for, matrices. We have a set for real numbers. We have a set for functions that are differentiable. We have a set, we've constructed a set for functions that are continuous. We have constructed a set for functions that are 2 times differentiable and all that. So we have sets for everything. So we also have what is known as the set of all linear applications, which is denoted by, the set of all linear applications is denoted by, this notation, the set of all linear applications from E to F. So if you see this, then what they are saying here is, this is equivalent to saying that F est une application linéaire. If you see this set, F est une application linéaire. Instead of, writing, this very long, phrase, all I have to do is to just use the symbols and say F appartient à l'ensemble des applications linéaires. So this is l'ensemble des applications linéaires. So I just forgot to sort of like, talk about this. Ok. Donc, soit E et F, deux cas espace vectoriel, et F, une application linéaire. Pour tout sous-espace vectoriel A de E, l'image F de A par F est un sous-espace vectoriel de E. So we'll look at that a little later. Now, look, this is what I was saying. On the previous slide, this is what I was saying. On the previous slide. I said, when we're talking about les ensembles, we talked about l'image directe. We talked about l'image directe. So we said that l'image directe d'un ensemble is, so where we have a parent space E, we have a parent set E, and then we take a subset. Okay, we take A. Now A is a subset of the parent space E. Then l'image directe, which is denoted by, this notation that we have here, F de A, is a set of all elements F of X, such that X is in the set A. Now, if I look at what we have here, we can now define what is known as l'image. L'image, in the case of les sous-espaces, in the case of les espaces vectoriels, we can define what is known as l'image. So all I have to do now look at what I'm going to do here. All I'm going to do now here to sort of like match what we have for les espaces vectoriels, what I'm going to do is to match what we have for les espaces vectoriels is I'm going to have what is known as l'image de l'application F. L'image de l'application F. So, for this definition that I have here, let me just maybe go back here. Instead of having f of A, and instead of having A and E as just, general sets or normal sets, A is a sous-espace vectoriel of E, and then E is an espace vectoriel. So, f of E is going to be what? If f of A is a set of all elements f of x, such as x is coming from A, then f of E is the set of all elements f of x such that x is coming from E, like so. It's as simple as that. Then this same set f of grand T, this same set f of E, which is the parent space, is what we'll call l'image de l'application linéaire. C'est clair? L'image de l'application linéaire, c'est quoi? It is the set f of E such that it is a set that is denoted by, this f of E, or l'image de f as I've written on the left hand side, such that, is a set of elements f of x such that x is coming from the set E. So that's like the analogy that we have between, les espaces vectoriels, what we looked at, in les ensembles, and then what we're talking about here in les espaces vectoriels. So l'image de f is precisely, this set that I've represented here. L'image de f is precisely this set that I've represented here. So saying, in case maybe you don't understand what I've written here, in case you don't understand what I've presented here, saying, if I say y is an element in l'image de f, y is an element in l'image de f, simply means that il existe x, there's some element x that is in the set E, tel que y is equal to f of x. So this is what this notation means. So l'image de f is equal to this set f of E, then is a set of all elements f of x such that x is in E. So if I say z is in l'image de f, I'm saying that il existe x prime in E, tel que z is going to be equal to f of x prime. La même chose, if I say w is an element in l'image de f, then I'm simply saying that il existe x prime prime in E such that w is going to be equal to f of x prime. Like so this is what I'm saying. So this is what the set l'image de f is. So any element you take from l'image, meaning we can find some corresponding value for x in the espace E such that y is equal to f de E, f de x. So l'image de f is precisely this set that I've written on the right. L'ensemble des éléments f de x tel que x is an element of what? X is an element of E. Meaning any item I take from l'image de f, it means there has to exist a corresponding vector x in what? In E, because we're talking about les espaces vectoriels. Any element in l'image de f, any element that is in l'image de f, there must exist a corresponding value for x such that y is going to be equal to f of x, where y is an element in l'image de f, and then x is a vector in what? X is a vector in E. So that is what l'image is. Now look at what we're going to do here. This same set that we've defined a new set. We're from defining a new space. We're from defining a new set, which is l'image de f. Now l'image de f, I'm going to show that l'image de f est un sous-espace vectoriel de f, where f is another espace vectoriel, because we have f a mapping from what? From E to f. So we've defined a new set. We've defined a new set which is known as l'image, which is precisely this set that I've written here. We've defined a new set. Now we want to show that the same set that we've defined, which is l'image de f, est un sous-espace vectoriel of the codomain, which is the second espace vectoriel, which is f. So montrons que, that's what we want to do here, montrons que l'image de f est un SEV de f. So how can we show that l'image de f est un sous-espace vectoriel de f? So let's first of all remind ourselves, what we're supposed to do here for us to show that l'image de f est un SEV, est un sous-espace vectoriel de f. What are we supposed to do? Well, the first thing that we're supposed to show is that l'image de f is non-empty. So the first thing that we're supposed to show is that l'image de f is non-empty. Now, this one is c'est trivial. So c'est trivial that l'image de f is non-empty. Why? Let's look at what we, a property that we can use to sort of like, think about this. So we talked about this property. If you remember, f est une application linéaire. So f is going to transport the zero element of e to the zero element of what? To the zero element of f. Now let me write it in another way. Now this is, we can write it as 0 de f is equal to f of 0 de e. Now we know that this 0 de e is an element of e. And then we also know that this 0 de f is an element of what? Of f. If you look at this statement that I've written here, if you look at this element that I've written here, I mean the first statement I've written here, the whole lot of this statement that I've written here, this is like your y, right? This is like your y, and then this is like your x. Okay, this is an element here, in here, and then this is an element of this particular space. So here we have the form y is equal to f of x. So we see that this 0 de f is an element of what? Of l'image de f for 0 de e, which is an element in f, in e, like so. So, par linéarité de f. So this property is par linéarité de f. We have this. F est une application linéaire because we said this is a necessary condition. If f is a linear application, then it transports the zero element of the domain, which is l'espace E, to the zero element of the codomain, which is l'espace f. So here we have the form y is equal to f of x. So it means that this 0 de f is an element of what? Is an element of l'image de f. Because by definition, that is what l'image de f is. Y is an element in l'image de f if we can find some value for x such that y is equal to f of x. So this is what we have here. So for the value of y 0 de f, we found il existe une valeur dans e, which is 0 de e, tel que 0 de f est égal à f de 0 de e, which is y est égal à f de x. Meaning, 0 de f est un élément is an element in l'image de f. So, because l'image de f contains the zero vector or this zero vector of f, alors it is non-empty. So remember that to show that a particular space is non-empty, we have to show that the identity element of the parent space is in l'image of the space that we're trying to sort of like check if it's a sous-espace vectorial. So we know that the identity element of f is 0 de f. So we have to show that this is in the space l'image de f, so which is what we've shown here, because 0 de f est un élément de l'image de f, because we have the form y est égal à f de x. That is what, that is what it means for y to be an element of l'image de f. Y is an element of l'image de f if il existe x tel que y est égal à f de x. In this case, our y is 0 de f, and then we get this property. This property, we get it par linéarité de f, because this is a condition. This is the necessary condition. This is the necessary condition for, that every linear application is going to sort of like satisfy. Okay? So we've shown that l'image de f is non-vide. What is the second property? Well, the second property we are supposed to show, if you remember very well, is we are supposed to show stability by addition. Supposed to show stability by addition. Okay. Let's look at how we can do this. So remember, we say that you take two elements from the given space, space. So soit we take two elements from l'image de f. We take two elements from l'image de f. So we say soit u et v. We take two elements u and v in l'image de f. Okay? We take two elements u and v from what? From l'image de f. So we take two elements u and v from what? From l'image de f. Okay? We take two elements from l'image de f. So what does it mean for... So let's first of all write our goal. What is our goal? Our goal here is to show that the sum, which is u plus v, we're supposed to show that u plus v is in l'image de f. That's what we're supposed to show. Stability by addition. That if I take any two elements in l'image de f, and I add them, I must get an element in l'image de f. So what does it mean for u to be an element of, l'image de f? It means that il existe x dans E. We can find some element x in E tel que, because l'image de f is this set. If you are wondering why E and not f, it's because remember that I said that l'image de f is this set. L'image de f is also equal to f de E, which is the domain, and then it is precisely the set that is on the right that we have here. So by definition, so u is in l'image de f if we can find some x such that u is equal to f of x. So what does it mean for v to be in l'image de f? It means that il existe y in E tel que v is going to be equal to f of y. This is what we've said. Okay? So let's look at the sum. Well, the sum u plus v is going to be equal to f of x plus f of y. That's what the sum is. The sum u plus v is. So let's look at the sum. Now that we have everything, let's now look at the sum. Let's look at the sum. So we have this x and then we have this y. So let's first of all look at the sum between x and x plus y. Now the sum between x plus y, if you look at this x plus y I have here, then I apply f to this particular function. If I apply f to x plus y, because f is a linear application, I'm going to get f of x plus f of y, like so. I'm going to get f of x plus f of y if I apply f to the sum x plus y. Now let me, in case, maybe just write something to make you remember when you sort of like, get back to this point to sort of like see, what I wrote and how I sort of like came up with, whatever is going to follow. So x and y are elements of E, right? X and y are elements of E. So this item x plus y is in E. Well, this is because E is an espace vectoriel. Now let's apply the function f to x plus y. Let's apply the function f to x plus y. So if you apply f to x plus y, what are you going to get? Oh, if you apply f to x plus y, because f is a linear application, you have that you're going to get f of x plus f of y. This is par linéarité. Par linéarité, like so. So we get this because f is a linear application. Oh, we have, f of x plus y. And then what is f of y? F of y is equal to u. F of x is equal to u. And then f of y is equal to what? Is equal to v, like so. Now, let's look at what we have here. So here we have u plus v is equal to what? F of x plus y. Now what does this mean? This implies that u plus v is an element of l'image de f. Because if you look at what we have here on top here, u is equal to f of x. If you look at this, u is equal to f of x. On the other side, you see that u is equal to f of x if u is an element of l'image de f. Same thing. V is equal to f of y if v is l'image de f. So we have a similar thing here. We have a similar situation here. We have u plus v is equal to f of x plus y. So this means that this item u plus v is in l'image de f. And then this is exactly what we are looking for. This is precisely what we are doing. This is precisely what we are looking for. Because that's our goal. We've taken two elements u and v from l'image de f, and then we've shown that the sum is actually in l'image de f. So l'image de f is stable by addition. So what is the third property that we're supposed to show? The third property is stability by scalar multiplication. Stability by what? By scalar multiplication. Stability by scalar multiplication. Let's look at stability by scalar multiplication. So how can we show stability by scalar multiplication? Remember what we were doing. So we're supposed to take lambda in K. So maybe let me just use a different color like so. So if you look at what we're supposed to do here, it's a sample. we're supposed to take a scalar. So soit lambda in K, and then we choose some vector U in what? In l'image de F. Then let's not forget our goal. Our goal is to show that lambda multiplied by U is an element of l'image de F. That's what we're supposed to show, that lambda multiplied by U is an element of what? L'image de F. This is what we're supposed to show. Okay. What does it mean for U to be in l'image de F? So this means, this is equivalent to saying that il existe, we can find some element X in E tel que U is going to be equal to F of X. Like, so we can find some element X in E such that U is going to be equal to F of X. This is what it means. This is what it means. Now we know that lambda multiplied by X is an element of E. Lambda multiplied by X is an element of E. Why? X is an element of E, and then E is an espace vectoriel. So if I multiply the scalar lambda multiplied by X, I'll still get an element of E, because E is an espace vectoriel, and then it is stable by scalar multiplication. So this item lambda multiplied by X is an element of what? Of E. Then let's apply F on lambda multiplied by X. So F applied on lambda multiplied by X gives us lambda multiplied by F of X. This is par linéarité de F, because F is a linear application. So F of lambda X is equal to lambda multiplied by X. Oh, this item that we have here. This item that we have here, F of X is equal to U. F of X is equal to U. So this is going to mean that lambda, we're going to have lambda multiplied by U, because here we have U is equal to F of X. Okay? So here we have F of lambda X is equal to lambda multiplied by U. So in other words, we have lambda multiplied by U is equal to F of lambda of X. Oh, this is an element of E, just like I said. This is an element of E. So in other words, we are saying that lambda multiplied by U is an element of l'image de F, because we have the form Y is equal to F of X, where the item here in brackets is an element of the domain. So we've checked all the three conditions. And then all that is left for us to do here is to conclude that l'image de F est un SFV est un sous-espace vectoriel de quel espace? De F. Oh, because l'image de F est un sous-espace vectoriel de F, c'est bien un espace vectoriel. Because a sous-espace vectoriel is also an espace vectoriel. So this is what we said. So hopefully this part is clear here. Now, of course, you have the recorded session later on, so you can sort of like rewatch this particular section if it's not clear, and then you'll be able to understand what is happening here. C'est bon, je passe. Is it clear? We look at something else. Okay, now due to time, what I'm going to do is sort of like simplify what I'm saying here, and then you'll be able to rewatch the video and see how I came up with, with these ideas. Now the takeaway here is that l'image de F, if you see l'image de F est un sous-espace vectoriel of the codomain, which is F. That's what I want you to remember. L'image de F, c'est un sous-espace vectoriel de quel espace? De F. L'image de F est un sous-espace vectoriel de F. And then if I say Y is in image de F, then what it means is, if I say Y is in l'image de F, then what it means is that we can find some corresponding X in E such that Y is equal to F of X. So Y is in l'image de F if I can find some corresponding X such that Y is going to be equal to F of X. So this is the takeaway. And then you can sort of like rewatch this part to understand the demonstration. Sinon, je vais définir le noyau. So let's now define what is known as le noyau d'un espace vectoriel. Le noyau, which is cœur, the kernel. Okay, le cœur or the kernel. Okay. And then we'll summarize. And then we'll look at injectivity, and then we can look at the exercises some other time. Up, like so. So what we're going to do is, maybe after just discussing the noyau, then we'll come and do the exercises. Some other time, so that I give you time to watch and the others to watch, so that we can now do the exercises and sort of like understand everything that is happening here. So let's look at the last part here, which is le noyau. Ok. Donc, soit E et F, 2K espace vectoriel, et F, une application linéaire de E dans F. L'ensemble des vecteurs de E qui ont pour l'image 0 de F par l'application F est appelé noyau de F, et elle se note ker de F en d'autres termes. So in other words, everything that they've written here is sort of like packed into this concise mathematical expression or equation that we have here, or definition that we have here. So just l'image de F is a set. Even the noyau is also another set. So the noyau is the set of all elements X in E, such that those elements have the zero vector of F as the image. So any vector whose image is the identity element of F. Now remember here that F is a mapping from E. F is a mapping from E to what? F is a mapping from E to F. So any vector in X. So here we are saying that any vector in X, any vector X in E, whose image is the zero vector of F, is going to be in this ker de F that we've written here. What do I mean by image? So we have the domain, which is E, and then here we're taking elements X. We were taking an element X in E, and then the image is going to be contained in F. So every element X here is going to have a corresponding value F of X that is going to be in F. This F of X is what we are calling l'image. Now, if for a particular vector X, the image is the zero vector of F, if let's say this F of X is equal to 0, the zero vector of F, then this vector X is going to be in the kernel or in the noyau of l'application F. So a vector X is going to be in this espace. C'est aussi un sous-espace vectoriel, but this time c'est un sous-espace vectoriel de E. So this X that we have here, this X, the vector X that is an element of E is going to be in the kernel if the image of that particular vector X is going to be the zero element of F. The image is this item F of X. So here we are saying X is going to be in the noyau or in the kernel if F of X is equal to the zero element of what? Of F. Is the definition for le noyau clear?
Yes, it is.
Great. So that is what we have here. Now at this point it should also be clear that this kernel is never empty. The kernel is never empty. Now why? Why is the kernel never empty? Who can maybe try to sort of like look at everything that we've talked about so far and connect it with what we are talking about now, and sort of like deduce that the kernel is never empty. So the kernel is never empty. Let me even write it in red as a comment. The kernel is never empty. The kernel is never empty. The kernel is never empty. Why is it never empty? C'est simple. Par linéarité de F, what do we have par linéarité de F? We know that the F that we're talking about here, the application we're talking about here is a linear application, right? So that necessary condition has been what? Has been checked. The necessary condition has been checked. So par linéarité de f, par linéarité de f, we have that f of 0 de e is equal to 0 de f. This vector 0 de e, which is an element of E, has its image is what? The image of 0 de e is what? Is the zero vector of f. Is the zero vector of f. And so this vector 0 de e is in what? Is in the kernel, because its image is 0 de f. So any vector that has image, any element x in E that has whose image is going to be 0 de f is in the kernel. If you look at what we have here par linéarité de f, the necessary condition that every linear application satisfies here, if you observe what is happening here, you can see that this 0 de e, which is an element of let me just first of all work on the network. Okay, it's back. Yeah. So if you look at this 0 de e, this element 0 de e, which is an element of E, or which is a vector in E, its image by the application f is 0 de f. So it satisfies this condition that we have in the kernel. And so the kernel is never empty because it contains the identity element of the espace E. So the kernel is never empty because it contains the what? It contains the identity element of E, because that is going to be satisfied or verified par linéarité de quoi? Par linéarité de f. So the kernel is never empty. That's the conclusion that we can draw here. The kernel is never what? The kernel is never empty.
Okay. Can we also say that the kernel is never empty because it always contains the zero vector? Is it also right to say that?
Yes, that's what I'm saying, because the zero vector. But what zero vector are we talking about? It's a zero vector of what? Of E. So it's the same thing. It's the same. Yeah, it's equal to what I'm saying. So the kernel is never empty because it contains the zero vector of what? Of E. Now, how do you show that the zero vector of E is in the kernel? You simply use this property that we have here par linéarité de l'application f. You look at that necessary condition that every linear application is going to satisfy. You look at that, you inspect it, and then it is from that particular property that our answer, that our response, that the verification that the kernel is never empty, that's where it's going to come from, the verification. That's where the verification is going to come from. So very, very important, piece of information. The kernel is never empty. And what is going to follow next? What is going to follow next is, since we've shown the first condition of something, we have to show the other two conditions that are remaining, and then we can conclude that actually the kernel is c'est un sous-espace vectoriel de E. And so since it contains the zero element of E, so it makes no sense to show that it's a sous-espace vectoriel of F. It makes more sense to show that the kernel is an espace of a sous-espace of E, because it contains the identity element of E. So the work has already started here for showing that the kernel is a sous-espace vectoriel of E. So we've already started the work. Let's look at the other two properties. If we check the other two properties and things work for us, then the conclusion is going to be that the kernel is a what? The kernel is a sous-espace vectoriel of E. And because it's going to be a sous-espace vectoriel, it's itself going to be an espace vectoriel in of itself. Okay? So let's continue with our work. So now we have to montrons que le Ker de F est un SEV de E. We have to show that le Ker de F est un sous-espace vectoriel de E. What are we supposed to do? Well, the first condition has already been checked. We've already, shown that the kernel is non-empty. The kernel is non-empty. The kernel of F is différent de l'ensemble vide, car we know that the zero element of E is always going to be in the kernel. The kernel is never empty. Now let's sort of like look at how we can go about, showing stability by scalar addition. Stability by addition. Stability by addition, c'est très très facile. So what are we supposed to do? So stability by addition. Stability by addition. So c'est très facile. Just like we did for the we sort of like proceeded for the previous problem. We'll do the same thing. So we take two elements from. We take soit x1, x2, two elements in the kernel of f. Now let's not forget our goal, because we cannot solve a problem without knowing where we're supposed to sort of like arrive. Okay, we cannot start a problem without knowing its destination here. So the goal here is to show that the sum x1 plus x2 is in the kernel of f. That's our goal. Okay, so let's first of all understand what it means for x1 to be in the kernel of f. So let's understand what it means for x1 to be in the kernel of f, and what it means for x2 to be in the kernel of f. So x1 is in the kernel of f. This is equivalent to saying that f of x1 is equal to the zero element of f. Okay, f of x1 is equal to the zero element of that. And then what does it mean for x2 to be in the kernel of f? Well, this is equivalent to saying that f of x2 is going to be equal to 0 of f. Okay, that's fine. That's very okay. Okay, now let's look at the sum of these two items. Let's look at the sum. X1 plus x2. X1 plus x2 is an element of what? Let's look at, if we apply f on x1 plus x2, what are we going to get? Now, because f is a linear application, f of x1 plus x2 is going to be f of x1 plus, f of x2, like so. Or f of x1 is equal to 0 the f of x2 is 0 the f, and then finally we get 0 the f. So we see that f of x1 plus x2 is equal to 0 the f. What does this mean? It means that the image of this sum x1 plus x2, c'est le 0 de f. And so this is equivalent to saying that x1 plus x2 is in the what? Le cœur de f. So stability by addition, done and dusted. Third property, stability by scalar multiplication. C'est très facile. Stability by scalar multiplication. Okay? Bon. Remember, we have to say soit lambda in k, and then simple mal, you can take x in the kernel of f. Now let's look at our destination. What's our destination? What's our goal? The goal is to show that lambda multiplied by x is in the kernel of f. Okay, before we even sort of like do that, let's understand what it means when we say x is in the kernel of f. So x is in the kernel of f. This is equivalent to saying that f of x is equal to 0 de f, like so. Now I know, let's look at, if I apply f on lambda multiplied by x, we're going to get lambda multiplied by f of x, car f est une application linéaire. Because those two conditions, remember them, f est une application linéaire. Okay, we have f of lambda multiplied by x. So lambda, now f of x is 0 de f. So 0 de f. And then lambda multiplied by 0 de f, it's, now you've guessed it right, it's 0 de f. Like so. Now what does this mean? It means that the image of this vector, lambda multiplied by x, is 0 de f. And this is going to imply that lambda x is an element of cœur de f, because all the vectors in cœur de f have their image by the application f is going to be 0 de f. Now that we've shown all the three conditions, the kernel is non-empty, we have stability by addition and stability by scalar multiplication. Now that we've shown all those all those three properties, il reste à conclure. So all we have to do is to conclude that le cœur de F est un sous-espace vectoriel de quel espace? De E. Because a priori, it contains the zero element of what espace? Of quel espace? Of l'espace E. It contains the zero element of l'espace E. And so a priori, it is going to be, a priori, that is, it contains the zero element. And then it is therefore going to be a sous-espace vectoriel of E. Because a sous-espace vectoriel is an espace vectoriel, so we can say that le quart de F est un espace vectoriel. So, l'image, c'est un sous-espace vectoriel de F. Le quart de F, c'est un sous-espace vectoriel de E. That's what the difference is. L'image de F est un sous-espace de quel espace? De F, which is the code domain. If F is an application, if small f is an application from l'espace E to l'espace F. L'image de F est un sous-espace vectoriel de quel espace? De l'espace F. Le quart de F est un sous-espace vectoriel de E. Okay? So, that's how you can sort of like show that le quart de F est un sous-espace vectoriel de E. Ça marche? C'est bon?
Un peu.
Okay. Natasha?
It's okay, I'm good.
Okay. So, voilà. So, we'll do the exercises. Some other time, maybe tomorrow or the next time we have the session. Or we'll look at a lot of exercises so that you understand these things. And then I'll also add, I'll also connect the somme direct, what we did for la somme directe et les espaces supplémentaires. We'll also combine that with what we've talked about here. For some exercises, we'll show that l'image is going to be on somme direct with le cœur de F. We'll look at all those things, and then how you show injectivity, how you show surjectivity, and we'll look at one very fundamental theorem in linear algebra, which is le théorème du rond. We'll look at that, and then we'll see how we can sort of like apply that in exercises, and see how we can answer questions using those techniques and things like that. So, je vais laisser ça pour la prochaine fois. Et on va s'arrêter ici. Bien, si vous avez des questions, n'hésitez pas. Do you have any questions? Est-ce qu'il y a des questions sur ça? Des questions? Le cœur, l'image. Quoi d'autre? Les applications linéaires. The necessary condition. C'est bon?
Yeah, it's just a bit. Maybe. So, like, is the topic then for les applications linéaires?
Les applications linéaires, if we do exercises, and the other small part, les hyperplans, we look at the hyperplanes and all that good stuff. And then maybe you understand all those things well, if we sort of like do more exercises. And that's how I sort of like expect that we sort of like conclude this particular topic. Les exercices sur the things that we've talked about. That's the only thing. Maybe we do, more exercises, maybe 10 exercises on the same thing, then you'll be able to sort of like understand everything.
Okay, I'm also just suggesting it maybe when doing exercises, we can also do some my TDs.
Yeah. You can maybe send me your TDs in advance before maybe. Yeah, you can send me like over maybe today or tomorrow. Send me the TD so that I compile everything in compile what you're going to send me and with what I have, so that we can sort of like have one document we are looking at.
All right. Yeah, we can also do the same for mechanic.
Yeah.
All right. Thank you.
Okay. Bien. Alors, on va so you are free to exit the meeting. C'est tout pour aujourd'hui.